Hi, welcome to the lecture Spectrogram, Cepstrum and Mel Frequency Analysis. In this lecture we will talk about spectrogram, Cepstrum and Mel Frequency Analysis and Mel Frequency Capsule Coefficient. So let's talk about spectrogram first. In the previous lecture you should have understood that the speech signal is analyzed over short analysis windows, and then in each short analysis window it goes through FFT and then you get the spectrum out of it. So this process is repeated for all the analysis windows, and thus a speech signal is represented as a sequence of spectral vectors, which you can see here. So let's understand a bit more out of it. Sorry. So there is a speech signal and there is a short analysis window. It goes through FFT. You get the spectrum here. So this spectrum is what you are seeing as a yellow rectangular box is essentially something like this, where there is a frequency axis on the x-axis, and then there is amplitude here, and then these are the peaks in the spectrum, and then you get the line connecting out of it. So this is the spectrum which you are seeing for each of the yellow rectangular box. So let's just try to flip it up by 90 degrees like this. So we haven't done anything much except turning it to 90 degrees. That means on this direction we have the frequency axis, and on this direction we have the amplitude, and that's how you're seeing the spectrum here. So let's just do something more. So take each of these spectral value or spectral amplitude and then map them to a gray level value ranging between 0 and 255. 0 represents black and 255 represents white. So if the amplitude is higher, that means the darker would be the corresponding region. So you can see the same thing here. So each of the spectral amplitude gets mapped to a gray level value. Gray level value is something ranging between 0 and 255. 0 means black, 255 is white. So this is the peak here. So this is higher the amplitude, that means the darker would be the corresponding region. So if you see this point here, so this is the 0 level, and then that's where you get white color here. So similarly these shades, gray level shades, indicates that the peaks are in between. They are not too high and then they are not too low either. So that's how a spectral amplitude is being mapped to a set of gray level values depending on the height of the amplitude here. So this is a convenience representation rather than anything to do with the processing or the effect of it. So because this is a three-dimensional, and then so that means there is a frequency, there is an amplitude here, and then so instead of representing in this direction, so you just represent a convenient way of doing it. Let's understand why we are doing this in a moment, but for the time being understand that each spectral amplitude is being mapped to a gray level value. So if you do the same process for all the spectrum, you would get a sequence of blocks like this, where the time axis is where this horizontal axis is the time and the vertical axis is the frequency. So you can treat this as time frequency representation of the speech signal, which is referred to as spectrogram. Please note that we started with the speech signal, get the spectrum, and then the spectrum is being denoted as or the peaks in the spectrum has been denoted as the dark and white regions. So dark is a peak and the white is a non-peak. So if you denote that way, so each spectrum gets mapped to another block like this. So you have a sequence of spectral vectors represented using gray level values in the time domain. So this is a sequence going in this direction, and because the frequency is in this direction, so this is referred to as time frequency representation of the speech signal, and this is known as spectrogram. So let's see some real spectrograms, why we are talking about them. So this is a speech signal here, and then this is the time axis, and this is a frequency axis, and this is a spectrogram corresponding to this speech signal. So you can see that this line striation which you are seeing here is obtained by using a short analysis window at this point and then plotting the spectrum and then mapping the spectral amplitudes to the gray level values. So that means that if there is a dark region here, there is a peak at this frequency axis at this point of time. So you can see a lot of dark regions. You can see even here, here, and here, and here, and here. So these are all indicates the peaks in the spectrum. So why we are bothered about spectrograms? If you observe carefully, that phones and their properties are better represented in the spectrogram. Let's see why we are saying that. A simple example is that if you want to mark a phone boundary or like detect the endpoints of the phones in this signal, you can detect a point here, and you are not sure about this point, but you can definitely point here and then point here, point here, point here. So but this ambiguity here you can clearly gets shown in the spectrogram here. So you can see that this entire segment which you are seeing here has got two different sounds. So you can clearly see a boundary here. That's basically because this segment doesn't have any of these components here. There are no dark regions. That means there are no peaks in the frequency range of this region, whereas for the other sound you have got a lot of frequency components in the small or in this frequency region. So you can detect phone boundaries easily. That's one of the properties of the spectrogram. Okay, so the other important thing what you can do is that the sounds can be better characterized by their formants and also by their transition. If you see, this is a formant, dark region is a formant, so and then you can see the transitions here which are being denoted with the blue lines here. So I'm not going to give more details than saying that this transition or the formant transition will help you to identify clearly the sound which has been spoken, whereas if you look at this signal you can't tell what sound it is, right? And then we did say that formants carry the identity of the sound, and what we are seeing in the spectrogram is that formants and their transition carry much more better identity in the spectrogram. So basically spectrogram is more useful to identify the sounds by the formants and their transitions. So models like hidden Markov models implicitly model these spectrograms to perform speech recognition. Just keep this point in mind, that spectrograms are the basis for these statistical models to recognize. So what we are seeing here is being modeled by the HMMs implicitly when they get trained on the speech. So what's the useful of spectrograms? First of all, they are time frequency representation of the speech signal, and many times spectrograms are a useful tool to study speech sounds, phones, and phoneticians use these spectrograms extensively to study the phones of a new language and write down their properties. So they are useful for visual study purpose by phoneticians. And statistical models implicitly model these spectrograms for speech to text conversion. And similarly, it's also useful in text to speech systems. Let's say if you have a text to speech system, a high quality text to speech system should produce a synthesized speech whose spectrograms should nearly match with the natural sentences or natural spoken sentences. So you would see lots of spectrogram figures in many of these speech books, and many probably in some of the tools you are going to work in the future weeks. So this introduction would help you to understand that it is a time frequency representation, and it's mostly used as a visual study purpose. So let's move to our another topic of the lecture, capstral analysis. So you would often hear about capstrum and capstral analysis. So we are going to talk about what we mean by capstrum. Many times we use in the speech recognition systems. So you are seeing a sample speech spectrum here. Please note that the horizontal axis is the frequency and the vertical axis is the amplitude, but if you take the log of it, that's denoted as decibels here. So it's the log amplitude which is plotted here. So again, we have been emphasizing that peaks are important. So peaks denote dominant frequency components in the speech signal, and these peaks are referred to as formants, and formants carry identity of the sound. So what we want to extract from the spectrum here, so we want to find out the peaks, correct, and at the same time we also want a smooth curve connecting these formats, so something like this. So our goal is to extract